Okay, so thanks a lot for the introduction. Also the possibility to say a few words about what we did in terms of endeavors in trying to build systems that are dependable, and especially highly distributed systems that are dependable. So what I would like to talk about is research that started quite some years ago, and I will talk about some of these results, but also what we did recently in this area. Okay, so in principle, all this is embedded into something that you have seen most probably millions of times, right? So objects act, they collect data autonomously. This means even sometimes without our knowledge, and also much more data is actually produced. Things are communicated, they are linked, data are combined. You try to extract information and knowledge, and then possibly do decisions in order to influence the processes you are observing. And this is the more diagrammatical picture. So you have some sort of process, you observe it, you collect the data, and then you make decisions, then you try to influence the processes. And you see this in simple control applications, of course, right? You try to control a plant or an object, but you also see this in humans, right? So you see whether humans behave correctly, and then you collect data, how often they did not behave correctly. You make a decision and then possibly try to influence the people to behave better. So this is the opposite, and you can look at social processes as medical and biomedical things going in bodies, and do personalized medicine, whatever. It's always somehow the same sort of structure. And what you expect, for one reason or the other, is that you have a predictable behavior. So you would like to rely on these systems, okay? And usually it means that you would like to have guarantees on some end-to-end properties of these systems. And why do you want this? I think the society will, if you believe the predictions of industry or not, but I think will increasingly depend on this sort of infrastructure. And you see this already around everywhere. And I think this predictable and dependable behavior is a key for the acceptance of these systems in society. And of course there are also applications where this dependability is directly obvious. Okay, in homes, if you have a home automation, it's only an annoyance if things don't work properly. In other applications, it's important. Mainly in detecting natural hazards, observing the environment, surveillance, disaster management, cars that are interacting and communicating. So here, the correctness of whatever you have been building is important. Factory automation, healthcare, personalized medicine. So these are typical applications where this correctness of operation is important. Now, this dependability and trust has many aspects, okay? It has also aspects that have been discussed already in the last 2 days, a lot in terms of security and privacy. So all those who hope that I will talk about security now, no, okay? So I will concentrate on a very specific area, and I will not talk about all the other things that could have an influence on the correctness of the application, but I will do some sort of more general comments at the end. So we and of course also many others worked on this area quite some time, and I just remember one project we did with actually Siemens, where it's not a very what would say, sexy project. Okay, we worked on these fire sensors, okay, and we tried to do them wireless, because if you install them in homes, that you don't want to have all the wires, and we designed with them a system that did a hop-to-hop communication. If there's a fire here, then the information is propagated to the whole building, and actually it was then finally a product. It was the first certified product on the market. And what was interesting to us is It was a tremendous engineering effort in order to get these things work reliably. After we did some sort of, algorithms and routing protocols and so forth. And now you could say if this would have happened at the university, it's clear because they don't know how to design these systems, but it was at an engineering company, right? So what are the reasons? So I list a few, and these are actually not the only reasons why things are not dependable, but a few I will concentrate on the rest. So this is just a system where you have a radio for communication, a memory, a microcontroller, possibly energy harvesting, and so forth. And if you have these systems in the scenarios I just talked about, they are under very high resource constraints, okay? So you have not a lot of computation, not a lot of memory, not a lot of energy, and the wireless communication should use very low power, low energy. And the experience is the closer you are working on these resource constraints, the more unreliable your system gets. It's not a theorem you can prove, but seems to be obvious because every non-determinism you have then leads to a failure. If you have enough resources, there's enough you have enough labor. And interference is one of the prominent sources of this. Of this. So let me make a comment. I think you can talk a lot about the correctness of software. This is one issue. Here, I suppose that the software, in principle, what you write, in terms of functional terms, is correct. But the execution of the software is not correct because you need more than just the program, right? You need resources to execute the program. And if there are not enough resources, the program will fail, even if the program was written correctly. Right? And one of the reasons for this sort of failures is the interference. What does it mean? Examples are there's one task running on a microprocessor. There are more tasks that are disturbing. There's not sufficient resources to finish the task in time. Therefore, you don't get the data in time. Therefore, the functionality is not correct. Same with memory. Your task uses a certain amount of memory, but the memory is shared between many tasks. So there may be a certain situation at some point in time where there is not enough memory available. In terms of communication, it is the same. So you do a low power communication. There are interferences from the environment. Communication doesn't work reliably. Therefore, your control algorithm doesn't correctly work. Okay, so what is the second reason that makes it very complex? In contrast to the classical area of, let's say, wireless sensor networks, many of these systems show a high degree of dynamics. Okay, it's not just that they collect data and then submit. They show a high degree of dynamics. Why? Because the environment changes. Therefore, the functionality of every of these components changes quickly. You have user interaction. You have switching between different modes. And one example is actually an example I will, at the end of the talk, a little bit more say about. Is what we do in applying some of the research results is sensing of mountain phenomena. Okay, so we have sensors distributed in the Swiss mountains. Okay, and the example here is we have acoustic sensors that are listening to the mountains and try to understand whether there is something bad happening. And so what do you do? Okay, you have these nodes. They are sensing acoustic events. Then this sort of events is transferred to some sort of base station. And it's only a short event. There's something happening. Now the base station obviously possibly gets more information for more sensors. So it decides whether there's something important happening. So it's not just the regular thing that is happening. So this is a decision possibly done here. Then there's a communication going back to the nodes. Please switch on other sensor modalities. Switch on a camera, switch on a GPS, something that uses more power. They do this, and then they submit not only a little bit of information, but lots of information in order to get more insights in what was happening. So this is a highly dynamic behavior, and the system needs to adapt to this. Right? And this is this is an additional source of non-determinism that makes this problem of interference difficult. So if you look at the general challenges, is you would like to have a system that behaves correctly in the sense of non-functional properties, right? Not that the C program is wrong. So you need to avoid this interference or to bound the interference formally. And all of this under the usual very strict energy constraints, right? So what does it mean? For example, the system in the mountains, but also everywhere where you deploy this, you don't want to have big batteries, or you would like to harvest energy, so you don't have lots of energy available. So what does it mean? If there's nothing to do, you should sleep very well, okay? And if you have something to do, you should do this efficiently, right? And this, together with this adaptivity I was talking about, also means if there's something important, you should wake up very quickly. And you should switch gears very quickly between something that needs low operation and high operation speed. And this is these are the challenges. And I will talk a little bit now, with the start of the presentation, on what can be done, what we did some time ago, and also recently to overcome these challenges, and then finally give a few examples where we actually applied this in practice. Okay, so let us start. So obviously we start with a specific scenario that I will now go through step by step in order to explain a little bit what can be done, what of course others have been doing, and what is the current status. Okay, so the overall scenario is we have some sort of a process, could be physical or could be also some other process. We have sensors, we have actuators that change this. We have a communication. The communication is via a wireless network. You have possibly some other computation node somewhere that do computations, and then you feed this information back. And the overall system should work somehow nicely, reliably with low resources. Okay, all the constraints I talked about. And so obviously it has several components, and I will go through various of them. I start with something we did quite some time ago on wireless network, and then go to more recent stuff on end-to-end properties. Okay. Okay, so let's start with the wireless network. Okay, so just these are two examples. Okay, this is the example I was mentioning on the fire sensors. Okay, these are the fire sensors. They are communicating to each other, and this is one of them. Okay, of course the battery should last a few years. Okay, despite of this, you have hard real-time constraints. A fire should be at the end after a second. Okay, the information. So you have hard real-time constraints. So hard real-time to you, it means that you should provide some sort of guarantee. It doesn't mean it should be fast, right? So you should guarantee a certain time. And this is what we do in the mountains. You have lots of sensors here, and they detect various events and also communicate to each other. So the communication, in order to save energy, is not to one central base station. They do this communication hop by hop. There are also wireless protocols like LoRa and others where you could do a direct communication over a longer distance, but they have a way too high energy consumption per transmitted information. Okay, so there's a long history of this, especially in the area of wireless sensor networks, where people try to do this, and this is the usual process. Okay, it's something that A would like to communicate to B, and then through a network, and then they try to find a path, and it transmits whatever information, the packet, slowly from A to B, hop by hop, and at some point it's B. For the networks we are considering are not that big. It's just for illustration purposes. Okay, so this is what people used and are still using, and but it doesn't work. Okay, at least not in these settings. Okay, what does it mean it doesn't work? Okay, let's suppose, because you have a low power setting and you have possibly interferences, right? Could be someone is closing the door, someone is, one of the sensors has snow coverage, whatever, right? And then possibly things are broken here, okay? So what is necessary in order to adapt the path? Okay, in order to adapt the path, you need to find another path, you need to detect your neighbors, you should exactly know your neighborhood, okay? And then you reroute, okay? What does it mean? The packets that are here, because they are on the way, now should be rerouted and should find their way back in order to go to another route, okay? And then what happens if there's now something happening here and here, okay? It cannot be excluded that is happening, right? Then you're in big trouble, right? So if this goes on and on and on, then packets are everywhere, and you have long queues, you have queue overflows, whatever. Now you can say this is an artificial problem. No, it is not. We have also deployed these systems in the scenarios we have, and this is what you see. Packets are then lost. They are for a long time in the network. They don't arrive where they should arrive. And this is also the experience from industry who's using these protocols in mobile, in homes and so forth. Okay, so the question is, can we expect that this construction works reliably and efficiently? No, we cannot. Okay, and also reflected in the fact that of course people try to verify this and to do some proofs on it, but it's of course impossible. Because the state space is way too large, okay, you have a huge space of possible routing paths, possible environments, cases. It's virtually impossible to do any reasonable bound or proof on the behavior. So what should one do, okay? I think one possibility if you try to verify something is to look at very complex problems and then to try to verify, and so the other possibility that if you have the chance to make things simpler, it's better to make them simpler and then to prove something about it, right? And so in this case, actually, this is what has been done. It's a relatively old work, but still people are heavily using it, and it's getting more and more popular. It's completely rethinking the way how you do the communication. Okay, so if you go back, what is the principle here if you do this? What the principle is that you try to avoid any sort of interference. Okay, if you because all of this is in a shared space where all the wireless signals interfere. Or at least many of them, and then, you do this communication, and then you do this one, and then you did this one and this one, so you avoid any sort of interference, okay, in order to do the communication. So it's like if I try to say something to someone in the back row, and you cannot hear me directly, I talk to you, and you talk to him, and then the information somehow finally ends up in the back row, right? Now, you could do it also differently, and instead of avoiding interference, you just make use of it, okay? So, in what way? So let's suppose that these are three people who are talking to this one. If they say something differently with different speeds, the receiver will not receive anything, right? Okay, because, well, all they talk simultaneously. It's just almost no possibility to extract information. But if they say the same thing at the very same time with the same speed, well, he can understand this. So if you say the same whatever sentence with the same speed and same pronunciation and whatever, then I can understand what you said, right? And even possibly with a very high reliability, I can understand this. And this is the principle you could also use, right? So it's called synchronous transmissions. The reasons are somehow why this works in the wireless space is related to an effect called capture effect, and there have been afterwards lots of people working on this, trying to understand this from a signal processing point of view, in which protocol it works. It works in the usual whatever ZigBee space, but it also works with Bluetooth Low Energy and with LoRa and at other protocols. Okay, so how does it work now? What can you do now? Okay, so let's suppose this one has information, would like to transmit this information. It sends it. This is still the regular thing. Okay, these three nodes receive it. Now, what they can do, they can now send the information they received at the very same time, okay, and transmit it. What is the effect? Okay, this one receives the message again, but these four nodes receive the message in addition, right? And then they do the same, okay, they repeat the message, and so forth. Okay, so you do a broadcast in the whole network, and the effect is what you want to have, okay? The information goes from A to B. It is, but the system does not have any routing, explicit routing, okay? There's also no network state because you just broadcast the message through the wireless network. Okay. And why is it reliable? Well, because of the redundancy. This one receives the message in principle 3 times at the same time. If one connection is less, then the other two will take over, right? If one of them is not working correctly, at least the other two are working correctly, so there's redundancy. And there's also redundancy because it not only receives the message once, but possibly also the second time because of the wave that goes back. Okay, so there's a high degree of inherent redundancy. So what is now the abstraction you can do in order then to prove something? Well, it's the abstraction that despite of the fact that you have something like a highly distributed system, the abstraction is like a wire. Okay, one is sending and the others are receiving. Okay, it's of course not possible like within a wire that the two are sending simultaneously, then you get a big mess. Okay, but it's really the abstraction of a bus of a single wire. So all the multi-hop thing is gone. Okay, so what you make a very clean abstraction that helps you in order to prove then really properties in terms of predictability and so forth. Yes.
Like a flooding approach.
A what?
It's like a flooding approach.
Yeah, it's a flooding.
Doesn't that take more energy?
Yeah. I will come to the energy aspect later. Okay. So what you can do now is you can build on top of this something that is somehow known, well known, how you design reliable systems in airplanes, in cars, and whatever. Okay, you now do the partition of this shared resource, which is a shared wireless space. You partition this in time. So here in between, this is the time going to right. In between, no one is working. All the units are sleeping, okay, just consuming a few microwatts. Just the clock is on. Then they wake up, okay. What happens at the beginning, someone is distributing the schedule of communication for the next short round or time frame, which is a host. And then those who receive this message, because they are somehow not completely off, and so they understand, well, now I can transmit my information, for example, in the first data slot. For this one says, well, first data slot is for node N1, and then N1 transmits the message in the network, okay? Then, because here, this other node, N2 knows the second one is mine. Okay, and then at the end, a new schedule is computed and distributed. Okay. So what does it mean? It's not a typical time-triggered protocol that is not adapted. It's highly adaptive. Why? Because the nodes can say here, what is my request? I have now a much higher bandwidth. Okay, I would like to transmit more data. This information is here used, and the new schedule is computed. That means when the next round starts. For example, if there is a node here saying, I suddenly have an interesting event, I would like to have 200 kilobit per second or more, then what the scheduler will do, it will say, well, in the new schedule, the next round is already here, or here, or here, or here. Right? So it just makes the schedule extremely dynamic, round by round. It's not a time-triggered one where you have something periodically going on. You can change the schedule from time to time. This is completely impossible in industrial protocols, wireless HART, and so forth, because Because they use time-triggered schedule, but in a distributed way. At first, you need to distribute the schedule very unreliably to all the nodes. They all need to understand that this is the new schedule. And if someone doesn't get it, then the whole system breaks down. So that means if you would like to change the schedule in something like wireless HART, it takes minutes, right? And not milliseconds. Okay, so this is what can be done. Okay, you make use of interference. Okay, you make at first the system more amenable to theoretical work. You do the partitioning in time, and then you have something as a substrate that you can use to have a system that works reliably, at least in the sense of the wireless system. Okay, so many things have been done by us and by others on this sort of idea, and I just would like to shortly say something about what you can do in order to guarantee real time on this basis, but not too long, just that you have an idea what can be done. Other things have been done I will not discuss. Because of the redundancy, at least from the experiments we and others have been doing, the probability that a packet does not reach a destination, of course, it's not 100%. It's smaller than 100%. But due to the redundancy and the way the system is done, it's almost an IID sampling of a distribution. So it's much easier to do predictions on energy. Okay, but I would like to say a little bit more about the real-time guarantees. Okay, so in principle, you have now a certain substrate. It's like a bus, and you would like to guarantee that if a node requests a certain data rate, that also the information the node uses is arriving at the destination under the deadline and timing constraints. Now, I sometimes get the question, why is this relevant, real-time constraints? Okay, who needs them? Okay, I think there are two answers. There are very few applications where you are interested in timing constraints, especially wireless control systems, right? You have some sort of a control system, and then you would like to prove stability, so you need to know something, how long it takes from the sensor values to the control algorithm to the activation. But in many other cases, that was also the main motivation for what we do, the timing constraints are related to the correctness of the system. If you have no timing constraints, then you may have buffers that overflow and lots of other ugly stuff. And as I said, if it can go wrong, it will go wrong once at some point in time, right? So because timing is very much related to storage, if you have no constraint on the timing, then you may run in buffer problems, right? So this was also the example of the long transmission of hop by hop from A to B, right? So if something is going wrong, someone does not know where to put the data. It receives data. Okay, buffer gets bigger, and then the mess starts. Right? Because then the bigger data, you need to communicate them faster because you have more data to communicate, and then things go out of hand. So reason for real time is not only the timing, but also the amount of data you have in the system. Okay, so what is the main difficulty is to understand when to start a new round, because this is important to know, and it's important to communicate. If this is a round where everyone is active in transmitting, it's important that they know when to wake up again, because in between they sleep. You cannot just wake up a wireless node. Right? Okay, if you try to wake up, you should listen all the time, and this is not possible, right? Because this takes too much energy. So they need to know beforehand when to wake up. Okay, so this information when to wake up is very important to actually generate. And just as a example, let's suppose that you have here three traffic streams, right? So 3 packets to transmit here and periodically again here, and this is the corresponding deadline. So within these 4 time units, they should arrive. And then 4 other packets should be communicated, and here again, periodically, and this is the corresponding deadline, and here 5 packets with a period of 15 and a deadline of 12. So now what you could do is you tell just the system, please do a new round whenever there's a packet to communicate. Okay, so you say, well, if there's something to communicate, just schedule a new round. Okay, what does it mean? You have lots of rounds, and they are not full. They are partly empty. And every round generates lots of energy, because they need to wake up, they need to communicate, and to sleep again. So the goal is to reduce the number of rounds, and instead of being greedy, you could, okay, this is just the example. So you do the 3 packets here, 5 packets here, 4 packets here. There's nothing then, you wait, and then you do the 3 packets here, and so forth. Now, it's better to delay things as much as possible, which is in contrast to as early as possible, right? So you do not a greedy schedule like EDF and so forth. You try to delay in order to be able to aggregate to rounds in order to minimize the energy. And actually this can be done. So instead of directly communicating these packets here, you wait some time. Instead of communicating directly here, you put part of them here. You don't do the rest here because you know these packets have still a deadline that is far away. But here there's something coming in addition. So you take these 2 here and these 3 here. So you see, you delay as much as possible, and therefore you fill the packets you have, the rounds, and you save energy. Okay? Yeah, so there, in principle, the methods you use are the classical real-time methods, real-time calculus, network calculus, EDF, and so forth. But the problems, of course, are a little bit different because the constraints are different. So what you have, okay, you have a new stream request in the scheduler. You do admission control. Can this stream request be really taken over, or will the system break down? If yes, you compute the start time of the next round, and then this is done. Okay, so I skip this, and if you look at this, then finally, okay, and you employ all the knowledge you have in terms of processing and real time, you can say this policy is real time optimal, so no one can do better, giving a set of requests with deadlines, and it minimizes the energy constraint. So if you think it's simple, no, not really. Okay, let me just look at one aspect, the admission control. So if in this round, a node says, I have now lots of communication to do, okay, and it submits this information to the scheduler, then actually the scheduler needs to test this, and it needs to do some fairly complex computations, okay, with ceiling and floor and additions and divisions and so forth. And these are the typical equations you always see if you do real-time analysis. But you should do this now within a short time bound and very efficiently because you have low power nodes, right? So what comes in addition is to really a deep thinking of how to find bounds on this time and how to do these computations efficiently. Okay, so this is now some experiments in order to see whether it works. You see this is the time. This is some initial phase where the different nodes submit their request. Then this is a stable phase. Every 6 time units, you transmit 50 packets. A new stream request arrives. You see the schedule is changing. A new stream request arrives. The schedule is changing again. A deadline changes. The schedule changes again. All this done automatically, dynamically, just based on the new requests. Okay. And here you see the execution time on a very low power and and not very powerful system, and it's relatively small. This is because of the data structures we use, and one can provide hard upper bounds on the execution time. Okay, of course, this you can do on lots of the available networks and try to see whether the system works correctly. So one thing I would like to point out here is the deadline success ratio in a network that's not done by us, okay? So there are lots of these networks around the world where people have test beds in order to test their algorithms and the way how they work. This is something in Germany. It has 94 nodes, okay, that are distributed. And the deadline success ratio is 99.97% on the network. Why not 100%? Because, of course, some packets don't arrive. Okay. Of course, then they miss their deadline and they are gone. And of course, the energy use is much less than this greedy scheduling. So now I come back a little bit to the question there was. Now you have seen a little bit about what one can do in order to improve the wireless communication and how to introduce real-time protocols on this. And the question is this really competitive in terms of energy and other things? So one thing you can do is, and as I said, you test this on various test beds and compare it with lots of other protocols that are state-of-the-art in doing this sort of wireless communication that do hop by hop. And fortunately for us, okay, what you see is that so this is the accumulated distribution function of the nodes that the average 99.97% of the nodes receive the message, and the minimum one is this. And other protocols have a very small minimal reception rate because some nodes are just hardly accessible. Okay, and also the duty cycle we need to have the same sort of communication between is much lower. Why? Because we don't rely on any statistical means of doing the wireless communication, but on time triggered, carefully planned, no interference with other packets. All this is working without any loss. And you don't need to find your neighbors. You don't need a neighbor list. You don't need to neighbor discovery. Nothing like this is necessary. The same, of course, also if you change the traffic rate. I was saying in many of these applications you would like to be adaptive. The same story. Okay, things are the data yield doesn't change. If you change the rate, you of course only need a little bit more energy. And this is completely different for other protocols. Okay, if you change the data rate, then the packet reception drops, right? Because they cannot adapt quickly enough to the rate change. Packets accumulate in the network somewhere. They are not delivered, and then the packet reception rate drops. Okay, if this is not enough to show, of course, there is also something that's very nice. That's a dependability competition. Okay, there also people do competitions. Okay, where protocols are compared. And how are these competitions done? Okay, they are yearly done in the context of a conference. Well, you have standard nodes. Okay, people can deploy their protocols. You transmit messages from A to B. And they try to disturb you in an unknown manner with lots of interference generated by some interference generators and on various frequencies and making things as ugly as possible. And fortunately, the best protocols use all these design principles I just presented in the recent years. Okay, so seems that this design principle is because of the simplicity. Is very good. Now, what are the metrics? So this is the results from 2017 because we only participated in 1 year here. Okay, and the other results I don't want to present. And I think the things are reliability. How many packets were received. Second one is how much energy the system used. And the last one is what is the latency. And interesting enough, the team number 5, okay, obviously us, otherwise I would not present the result, okay, is best in all three, despite of the fact that they should be somehow in conflict to each other. Because, and the reasons are, as I just explained, right? Less overhead in terms of energy because you don't need to maintain neighbor lists and all of this, which is increasingly hard if you have a changing environment. Okay, so, yes? Okay, the question of increasing network size. Of course, so if the network size gets larger, then the distribution causes more and more energy spent in lots of nodes. My answer usually is I don't want to, it does not make sense to have a single low power network that has a few hundred nodes. I don't know any application where this makes sense. I think in most of the networks, they are smaller, and you then hierarchically combine them. Okay, they may work on different frequencies. You aggregate on the next layer of, let's say, communication. You have some nodes that have more power, then you communicate via a wire or via some other wireless LAN, whatever protocol. So the scalability issue, I think, does not occur, at least not in the applications we have seen. You would not have a big building with a few thousand of this sort of whatever wireless fire sensors just connected to a single host. Okay, you never would do that for various reasons. Right? So you would have subnetworks, and for each subnetwork you do something that is highly reliable, and then you have some node that is in the power plug. Yeah. Yeah. Yes. So yes, it is, and several people did this. What you do is if you make your protocol dependent on these factors, you introduce additional state, and things may go wrong. So it's a trade-off. And for the work we did, it makes sense. I just said to at least to what we do in the group, no, we don't enter this, right? Because then it's a continuum until you are at the usual sort of processing. Because if you know the path, you could just do the forwarding along this path, the same way as we do the broadcasting. But then the success very much depends on the quality of your prediction, whether you can reach your neighbor or not. Okay, good. So. Okay, so it's done on hardware. So the next element I would like to talk about is the hardware. So let me talk briefly about this part, right? Because now this one is covered. Now let's talk about what needs to be done in terms of the processing and communication. Okay, so and this is actually this part here. So we also thought about this and on how to verify the behavior of the hardware-software part in terms of the communication. Okay. So usually what is done traditionally in order to make design simple and lightweight and whatever, you have a processor, and this processor as well does all the sensor data processing, whatever this means, and deals with the networking protocol. Okay? And what is the consequence? You have high interference. Okay, high interference between what we also do embedded learning, right? When you do lots of computations here, okay, we get the acoustic data, we do a lot of computations, and we have a very time-sensitive networking protocol. Okay, so if you do this on one platform, on one memory, one cache structure, whatever, you have lots of interferences that makes it very hard to prove that things are working always correct. So what we try to do is to somehow separate these things by an actual active interface and make them as much as possible independent. So this is one of the design principles, right? So if you have something that disturbs you, interference, okay, you should try to reduce it as much as possible, like in the wireless network case, but also here, okay? And then you may be able to apply formal methods to understand whether things work correctly or not. If you do this on the original design, I think there are also here lots of people, or Thiele is doing this and others, trying to understand worst-case execution times and so forth. This gets increasingly complex if your design is complex. So if you would like that it works correctly, maybe it's good to think about that. Okay, so just how does it look like? So there's an active element in the middle that contains all the interference that you cannot remove, which is actual data exchange. All the other interference on switching on and off the two processors, right? There's an interference on the energy, okay? If you switch off one, the other one would like to send data to this one that is switched off, data are lost. All this is gone because this interference we don't have. They can work on different power domains. They can be switched on and off completely independently. And the only thing that is in between is actually the interference that cannot be reduced because they would like to send something to each other. And so if you have this design, you can do tight bounds on the execution times. How do we do this? Nothing spectacular. You model the software. You do a worst-case execution time analysis. You model the hardware. You put everything into some model checker, and then you hope that what you get as worst-case execution times is close to what you can measure. And because the design is relatively simple, this is actually the case. So you proved timing constraints on the overall system. Okay, and it's low power. So if people say, well, this uses lots of additional power, it's in the area of microwatt. Okay, the initial interface is just a few microwatts, so this is extremely low. Okay. Okay, so the final part of the technical part, and then I go to some applications, is now end-to-end guarantees. Okay, so what we did so far is doing something on the wireless network and doing something on the computation nodes, right? So what they actually need to provide in terms of service and what they can guarantee. Okay, now end-to-end, we would like that really from here to here, information is correctly and reliably transported. Okay, so what are the challenges now? Okay, we know that this is working correctly, this one, and this one also, but we would like to have an end-to-end guarantee. You get sensor values, you process them, you transport them via this one. They end up in some other wireless interface, and they reach the destination. Okay, so end-to-end guarantees need to timely, adaptable. We would like to change things dynamically at runtime, and of course efficient. So how this can be done? Okay, it's a little bit a more recent thing. Last year, it's the same principle we had now applied to the overall system. Okay, so you plan things on the nodes, on the network, and put everything together. So what does it mean? One node does sensing. Then it transmits a packet via the wireless interface, via the network. It goes to some other node that does a computation, a message again via the network, and then goes to the other node, and this one does again some computation in order to actuate whatever needs to be actuated. Okay, so this is what we discussed, right? This is the message transmission on the network. It's happening in a round, and possibly this transmission is one of these, for example, this one or this one. Okay. Now you put everything together, and you need now not only to find a schedule on this communication system, but a schedule that combines what is happening on the computation nodes and what is happening on the network. So the overall overview is that you have an application model. So what you would like to operate. You have platform data. These are the data we extracted from worst case timing and whatever in your platform, on the network, on the delay in the network, on the number of rounds, and so forth. You do scheduling optimization offline, and then you move these tables to the system. Why offline? Because the scheduling problem is so complex, there is no chance to execute this and find a good... this is what you usually should not have, right? Not switched off your phone. Okay, good. And so these scheduling tables are then put on the platform at runtime. And how does it work? This is the application model. So what you can have are applications that consist of computations, communication, another computation, another communication, another computation. So you have a set of those, not only one. So lots of things that are running on your system with computations, communication, and this is what you would like to schedule overall with deadlines and so forth. Now, if you do this, you get to a completely static situation. Where is the adaptivity? So the adaptivity means that the system can be in several modes. Every mode has a different set of applications running. Here, application 1 and 2, 2, 3, 4, 5, 6, 1, 5, and so forth. So you are able to switch between... Remember this example with the adaptivity, right, on the mountains, right? So at first you are in a mode 1 where you're just listening to what is happening, whether there's an acoustic event, right? If there's an acoustic event, okay, you communicate and then you get the information from the host. Please switch on other sensor modalities. So as a result, you possibly go into a different mode where you switch on a camera, a GPS, whatever. So there's much more load on your processors. Okay, you get this information, and it's not only much more load on the processors, also more things to communicate. So also the load on the communication system is higher. Okay, so this is what I mean by modes. If you move from one mode to the next one, the system can look completely different. Okay, new tasks are arriving, others are gone, deadlines are changing, whatever. And this is also what you see here, right? So it's not that you optimize things for one situation, but you will be highly adaptive in the sense that that you have tables for every mode 1 table, and every node now knows, well, I should be in mode 1, in mode 2, 3, and then changes its behavior accordingly. All proven to be correct. Why? Because you do this offline. Okay. Okay, so after this, I go to the last half hour where I say a little bit about where we applied this stuff to small-scale experiments, a little bit funny, and also to large-scale experiments, right? Because of the work, how we do this, so try to do some advance in the methods and then to apply it. So one thing is a little bit related to cyber physical systems, to use this system to do a control. Okay, it was done together with, of course, like in many cases, other groups. In this case, Max Planck Institute on Intelligent Systems and some other group in Dresden, because it involves not only the communication system but also the control. Okay, so what do? We have physical processes, and then we have a controller that tries to control these physical processes. And actually, it's a toy example. As a control, we use what many people use as toy examples, inverted pendulums. Okay, you know this, right? So they look like, there's an example. They look like this, right? You have a card, it's an inverted pendulum, and you try to control this. And now we try to control this via a low-power wireless network. Okay, so this is somehow the task, and in the work, it's a combination of proving the control algorithms to be correct and stable under what we can prove about the wireless network in terms of end-to-end delay and jitter, and of course implementing this as a whole. So it's one part is the control part, which I will not talk about. The other part was designing this system here, putting all what we have together, and then really let it work. Okay. So just to say something about the jitter. So this is one thing people in control are concerned about, if messages arrive too late, too early, and what is the jitter. And these are the bounds. This is minimum and maximum in measurements, and these are the bounds we compute. So you see also, despite the fact that it's a large network with about 20 nodes, highly distributed, the jitter is quite low. Okay. So, well, this is the hardware containing this interface and all the scheduling algorithms and so forth. Okay. What you also can do, which is interesting, at least control people seem to like it. Okay. If you have several of these inverted pendulums, you can let them operate in synchrony, right? Why is this possible? Because all the information we have is global. Every node knows every sensor value and every actuator that is going on, so they can coordinate itself very, very easily, right? For people in control, this is something they like, okay? So the pendulums here, okay, this is somehow if you control them individually and try to let them do a sine wave, and this is if they are in synchrony, right? Because of the global information, this is easily possible. Okay, so this is now a short video on how it works. Okay, this is these are the individual sensor nodes. It's a multi-hop communication. They are the pendulums A and B. This one is actually controller 18. Here the control algorithm is running, and now someone takes it and runs around. Okay, this is now times 3 as fast as before, and the control doesn't change. Right? Despite of the fact that the controller is highly mobile and the network structure, the interconnection structure changes very quickly. It's still a multi-hop network. Okay, so let me show it again. Okay. Yes. So it's a multi-hop network. So if the controller is here, possibly the path to here is this one. Okay, but if the path may be different. So every time the node moves, the internet, the connection structure is different, right? Despite of the fact, nothing changes. Why? Because the overall protocol is independent of the interconnection structure, right? So this shows a little bit the robustness of the overall system. Okay, so final example is. Well, I talked a lot about trying to make things that work correctly, and okay, it's Switzerland, right? So Switzerland have these watches, and they also should go correctly, and so this is part of this. But it's also why we do this, because we are working on some serious applications. Okay, what does serious to mean? Okay, if you do research, there are 2 kinds of applications you can do. Okay, one is you have some crazy idea of an application. In your paper, you try to convince others that this is a very important application, okay? You write a paper about it, okay, and do some technical work. You do some small installation in your lab, and after the paper, you throw everything away, and you get to the next crazy application, right? And so this is not crazy and okay. An application where you convince people that this is a very important application. Right? So we do this very rarely. Okay, if we do experiments in the lab, they are mainly to test algorithms, to test the theory. But in terms of application, we decided to just have a few that are serious. What does it mean serious? Long term, and you work together with those who own the application. Okay, it's not a computer science application where you just say, well, this is important to the world, this is important to science, to society, but it's an application where you really work together with the people who are the owner of this application. Okay, and this is what we did, and where we also apply some of the stuff I just mentioned. And so if you try to do something that is highly reliable, should be highly reliable. It should be an application where this shows. okay? So at first it should be an application that where you can say, well, if the system doesn't work reliably, it has some bad effects, okay? It's something you would like to avoid. So it's a dependable application. And the other one that's also very important, if something doesn't work, it should be extremely hard to repair. Because otherwise, what you do is, you deinstall the system, then something's not working, you go there, you replace, you change the algorithm, you change the placement of your sensor so that it works correctly, and then you report this. Okay, okay. So here, what we do is we instrument mountains, okay, and obviously, if this is a sensor, and it's actually a sensor that is mounted here, to replace the battery, to change something is extremely expensive and sometimes also dangerous. So it's a very good application to say, whatever technologies we develop that seem to be useful in this application, we deploy it here in order to show that they do what they promise. So why do we do this? Okay, Switzerland is actually it's relatively south in Europe, but they have also lots of mountains, and in the mountains you see very often and increasingly often rockfall, and this rockfall actually has something to do with the climate change. Okay, we are doing all these investigations on levels above 3,500 meters. They were frozen beforehand continuously. Now they are sometimes frozen, sometimes not. So this causes some destabilization in the mountains. And why do we do this? We work together with people from geoscience. They would like to understand why this is happening, what are the causes, to model this better. And what we do is also used by the local authorities for early warning. Okay, so this is somehow what we do. And there are several field sites we are operating on the Matterhorn, on Jungfraujoch and other famous touristic areas also, but also non-famous areas because they are especially dangerous places in Switzerland. Right. So and you see here some of these sensor networks. Each node is a sensor, and they're distributed, and they are measuring various sensor modalities. This is just a Google image where you can see some of the communications. Okay, so just to give you an idea what is happening, this is a picture of 2009 actually from Matterhorn, and now you could focus on these three areas, and now this is a picture of 2015. If I go forward and backward, you see that many things happened, right? You see here there was some rocks that are fallen down. Same here, there's a larger rock that is fallen down. Okay, same here, this is 2009. The cracks open, and there are lots of changes happening, right? And sometimes these changes are so big that there's a rock fall, and there have been some recent events in Switzerland. Just besides, the other fun of this area is that you get lots of public attention, right? So recently there were lots of articles everywhere on these measurements and so on. Okay, good. Yes, so these are the sensors, and now you understand they need to work very reliably, and you don't want that the packets are somewhere in these sensors. They may be covered by snow, then the sensor is not working, but you don't want that the data that are there are gone, and so forth. Okay, so to give a better impression, so these are sensors, and as I said, some of them do acoustic sensing. Some of them are bigger, have cameras. We have also GPS sensors that actually do a precision of GPS of 1 centimeter with the usual GPS in your mobile phone. So also lots of algorithms are done. You have crack meters and so forth. And you have a base station on the mountain that collects the information with some energy harvesting. So therefore also did some work on energy harvesting. And you, of course, the backend server. So we have been working on the whole pipeline, and not only on the real-time aspects I was talking about, but also many other things can go wrong in the whole pipeline. So from the sensors, pre-processing, communication, data cleaning, understanding the geophysical processes, and do early morning. Okay, yes. So 10 years now. Lots of data points. Some of the batteries are lasting for 10 years, despite the fact that they're communicating every second. Okay, so these are, and this despite the fact that they are on sometimes minus 20 degrees, right? You see all these difficulties, right? If the temperature differences, if you are minus 20 degrees, the sun is shining, extremely steep temperature differences. So all these things with clock stability and so play a major role. Okay, yes, you can, all the data online, people are working on them. Yes, do you know who this is? Who knows who this is? Pardon? Me? No. No, it's Murphy, okay. So anything that can go wrong will go wrong, right? And actually, this is also our experience, right? So it's a time synchronization I just mentioned, right? Because in order to do these protocols, they need to be highly time synchronized, right? Communication disconnect, buffer overflow, energy harvesting, not enough energy harvested, sensor faults, whatever, right? So everything that can go wrong goes wrong. And we're working on several of these aspects and try to improve the technology. So, pardon? Pardon? The hardware, okay. No, the hardware, okay. The hardware is custom, yes, but not the chips, okay. We buy the components. But we put them together in a specific way. So the protocols, or the wireless protocols I was explaining, use conventional modulation schemes and so forth. Just the changes are on the, let's say, more computer science layer. Okay, so we don't change chips. We don't make our own chips. It's just standard hardware. Well, it's difficult to build robust custom hardware. Yeah, we have some experience in the meantime, yes. So this sort of research, if you try to also deploy the things you do in this sort of systems, it's quite some effort, yes. It also means that you need quite some funding for this, external funding. So many people help out with this, but it's you need a small engineering group who does, because you don't want that PhD students do this. Right. Yes, they should graduate with the research results and the papers and so on. Okay, so are there new threats on the horizon? This is the final thing I would like to mention. Actually, there are many. Okay, it's about energy harvesting, the sensor data from low-cost sensors. I could say a lot about this here, but I, for the sake of time, I don't do this because we also work in environmental monitoring, where you try to monitor air pollution. And low-cost sensors very often don't work, despite the fact that they're sold that they work. Okay, so it's also a question whether you trust the values you get. Okay, but one thing, just shortly, decision making on the edge. It's something that we use a lot, and we do complex sensing using acoustic emission. This is what I said. So we listen to the mountains. And if they don't feel well, they make noise, okay? Because if there's a crack, they make a click, okay? And this is something we monitor. Actually, we like this because it avoids any privacy discussion. Mountains don't complain if they are monitored, okay? Okay, good. But what does it mean, right? So we have our sensors. We have highly sensitive seismic sensors. So these are like microphones, okay? Wireless network data management, as we discussed. But what is the problem? Okay, this is how the hardware looks like because of your question. So this is custom-made hardware: the battery, the sensor, the wireless antenna, and so forth. So it contains all what I was explaining here. And why do we do this? Well, you get the acoustic signal, you get the frequency spectrum of the signal. And then you can analyze this. You can understand if similar things happen at various locations. And then you can combine the information and extract whether there is some some bad thing happening. For example, here you see this is a fracture meter that understands whether a cliff opens or not. It opens a little bit, and then you see here also acoustic events that are happening. And before really there's a fracture, so something falls down, you also have an increased number of acoustic events. Okay, so this looks great, but we are not the only ones making noise. Okay, you see there are some other people who are climbing, in this case the Matterhorn, okay, and it's a little bit better than on the Mount Everest. You have seen these pictures of Mount Everest where the people are piling up. So it's a little bit better on the Matterhorn, but not much. Okay, and you see here 1, 2, 3, 4, 5, 6, at least 6 mountaineers climbing up. Okay, what does it mean? What you measure here is not only what is the noise you are interested in, but also polluted, right? But it's also helicopters, it's rain, it's hail, it's whatever can pollute this. Now, if you transmit all of these data to the base station, you are dead. Okay. So what you need to do, actually, you need to do the decision whether it's something interesting. You need to move it from the final data processing as much as possible to the front, in order to avoid that you waste energy on something that is unimportant. Okay. So here I moved it actually to the sensor itself. This is something we also did, a sensor that does this detection itself. But mainly, you may also move it to the pre-processing. This is happening directly at the low power node. Okay. What should this do? It should distinguish, is this a mountaineer? Is this rain, or is it an interesting event? So what you do, you get the acoustic signal, you do a classification of the signal, and decide whether this is an interesting one or non-interesting one. Okay, so this is called actually embedded AI. Okay, so what you try to do is you try to classify acoustic signals, whether these are mountaineers, helicopters, wind, or hail, and extract the relevant information. And now, of course, it's not something we worked on, but it's definitely some question. It related also to what Rajiv was talking in terms of the control and verifying control. It's definitely a question. You do decision on the sensor node. If you miss the relevant information and classify it wrongly as a mountaineer, then the early warning system doesn't work. So you really do a decision on the node. And whether and how this has influence on the system, how you can prove this, that it's still okay or not, this is, of course, one of the threats. Okay, but there are, as I said, besides decision-making on the edge, there are many others. This will keep us busy for the next time. And before I come to the question, I just show the last slide. Okay, this is acknowledgement. So many people have been working on this in the area of algorithms, methods, verification, but also on the implementation of the systems. And this long list here with all the diagrams are all the people and companies who have given money to us, because it's also quite expensive research. Right? So even ETH Zurich is not able to pay for this. Okay, good. And it's, as I said, a cooperation between us, several institutes at ETH Zurich, Geodynamics, Federal Office of the Environment. This is a government institution, University of Zurich, and other institutions. Okay, mainly in terms of the applications in order to do something that makes sense. Okay, so this also ends my talk. This is just for your questions as a background, something the TV did in order to show what we have been doing. Okay, so that ends my talk. Yes, I think you had a question, yes. Okay, they can update it via the wireless interface. Yeah, so I think, Yeah, because the communication is somehow reliable, and you can also download the code via an update code via the wireless interface. Of course, you need to be very careful. Please don't update the wireless interface and the wireless protocol. But you see, the point is that you have these two nodes, right? So one is and two processors. One is responsible for the communication. The other one is responsible for processing the sensor signal. So we are careful in not allowing any update on the communication processor, right? Because this could break the communication. Right. Yes. For what? Yes. So this is a very difficult thing, right? So okay. Let's first talk about mountaineers, right? So if you would like to detect mountaineers and try to distinguish between the signals you get from the mountains internally and the mountaineers. And you would like to learn or validate a classifier, how do you do this, okay? So how we did this is to use a second source, which is a camera, doing classification of mountaineers on the camera, which is much more reliable because you can see people walking and colors and so forth. And use this as a ground truth in order to do the classification on the acoustic signals, which is much harder because you only have the acoustic signal and no image. Right? Still, it's still a question of if you learn a classifier, do a classifier, how to do this with not so many data. But this is the ground truth we get there. So the more difficult point is ground truth on precursory signs for any sort of rockfall, because rockfall is not happening too often. This actually is a combination of a few events that we happily recorded and modeling of the geophysical processes. So you get data, you model the geophysical processes, you have some idea what is happening as a precursory sign, and then you can validate this, not in the statistical sense, but somehow because you believe a little bit in the model and the few events, you can then get the information out of this. But this is much harder because there are not so many events happening. I think it's a little bit better in avalanches and so forth, but with rockfall is a little bit more difficult here. Yes. Yeah. Yeah.
My intuition is that if you map out all the parameters, like frequency,
Yes.
I mean, whatever parameters we have, that is a complex space, and probably glossy only points one point.
Yeah.
And there are many points in that space.
Yes, clear. Right.
So, it's clear where you want to be.
Okay. Okay. The question was yes. So it's yeah. You see, as usual, if you do a talk, you try to sell what you like. Okay. But of course, the protocol itself is not useful for whatever wireless communication you want to do. Right. I try to convey a little bit that it makes sense if you have power constraints. It makes sense if you have a multi-hop communication, and it makes sense if your network does not contain 1,000 unstructured nodes, right? In other cases, there may be many other things you can do, okay? So I know we also do this, combining different protocols and so forth. Yes, you have a question?
How often does it happen that the sensor was lost because the walk is falling down?
Yeah, so they are carefully, okay, so there was lots of, let's make a comment. There were lots of research also in the community how to place sensors, right, in order to optimally minimize energy. From our point of view, this is all nonsense, right? But why? Because you cannot just arbitrarily place the sensor somewhere. It's an interesting theoretical problem, but in practice, you need to exactly understand where to place the sensors. And they are placed at locations where possibly there is a rock above, so that they are not directly in danger to be hit by some falling rock, and they are placed in situations where you get hope to get interesting results, right? So far, I think, as far as I know, 1 or 2 have been lost, okay, due to this. Another problem is lightning, okay, that also can hit one of the nodes. And also what I was mentioning beforehand, if you do this, you need also quite some engineering knowledge. So they are in very solid housing and so forth, okay? It should be waterproof, whatever, right? So there are some things you do in addition. But so far, this is not a major problem. Of course, we lost also some sensors because some of them have been mounted on glaciers that are falling down, and so. Well, this was on purpose. Okay. Yes. Other questions? Okay. Yes.
You mentioned about the local bus and Yossi protocol.
Yes.
Being reliable. So, if there are multi-hop communications happening between sender and the receiver, and there are two senders or multiple senders in the system,
Yes.
there could be a possibility of interference even
Correct.
if there is one constructive interference happening from us.
Yeah. So the question is what happens if several senders are sending simultaneously, right? Okay. So what we investigated ourselves is if they are sending something at the same time, okay. This is working relatively nicely, right? Because then somehow one takes over and floods the other one. But it's a sensitive thing, and if you look for something that is reliable and that you can prove that it works, it's a little bit shaky, right? So yes, so that is the only thing I can say. So it works in practice relatively well, okay. That one takes over and floods the rest, and because of the capture effect, but it's theoretically a little bit shaky. Okay. Yes.
So you mentioned that resource allocation, the end-to-end.
Yes. Yes.
Do you see it going online
Yeah. No, I don't see this happening online, right? I think we know how complex these problems are, right? So we reduce it to the mixed integer linear programming problem, and it's really a complex problem because you have lots of applications running. You need to schedule the operation on the nodes and on the communication. The more challenging thing is the following: if you move from one mode to the next one, there's possibly a persistent application that runs here, and you don't want that this is disturbed. Okay, so it's not only that you somehow schedule everything fresh, but also you need to take into account persistent applications, right? So I don't think that this is possible, and you would also give guarantees, right? So how do you do this online? Okay, you should be able to give a guarantee that the system works afterwards. I think this is pretty hard. Okay, so I think in the quasi-static settings we have, that you know the different modes, that you know what are the requirements in the different modes. It is better to do this online, to have a table where you have all the information and then switch from one to the next one. And you can prove that these things work. You can prove that they work correctly under all of these settings. Because what happens if you would like to communicate data from the sensors to the base station and you don't know whether it's possible beforehand? And why don't you know whether it's possible? Because it depends on what was running on the system beforehand. So you cannot do any static guarantee on this. But you would like to do a static guarantee. You would like to know that if these nodes would like to send the whole data set to the base station, it is possible. So if you do this online, I don't see any chance that you can prove this. Right? So I think it's a combination of to be too complex and also not giving any guarantee. Right? you would like that this set of tasks is really feasible. And if you do it online, you don't know. Okay. Good.